Welcome to This Explainer. Today, we're going to impartially deconstruct a truly horrifying phenomenon that we keep seeing reported in the news from zones of heavy bombardment, this whole concept of evaporated bodies. Now, setting aside all politics, we're going to look strictly at the forensic science, the physics, and the thermodynamics behind these reports. We really want to understand exactly what happens to physical matter under these extreme conditions.
Okay, let's dive into this. Rescue workers and civil defense teams often use this colloquial term, evaporation, to describe the deeply unsettling experience of finding absolutely zero trace of a human being at a direct blast site. But if we zoom in and look at what happens biologically and chemically at the dead center of a massive explosion, we've got to ask ourselves, do bodies actually turn into gas?
Well, the scientific answer is no. Bodies don't just turn into gas in the traditional sense, like water boiling into steam. Instead, they undergo two simultaneous, absolutely extreme scientific processes. First, there's immediate thermal decomposition. Basically, this is the flash carbonization of biomass and the instant vaporization of bodily liquids. And second, there's total atomization. This is the micropulverizing of solid tissues and bone by just unfathomable pressure. To understand how this all actually happens, here's our roadmap for today. We'll start with the body evaporation phenomenon itself, then break down blast dynamics and shockwaves, look at aluminum's role in explosives, check out the Mark 80 bomb family, compare thermobaric to traditional explosives, and finally detail the exact impact an explosion has on the human body.
All right, let's kick things off with Section 1, the body evaporation phenomenon. So, field reports consistently note the complete and immediate disappearance of human biomass at the exact centers of heavy airstrikes. I mean, they find no visible traces, no bones, and absolutely zero DNA left behind. And while evaporation is a powerful and honestly a very popular metaphor for this sudden disappearance, the reality, well, it requires us to look really closely at the terrifying physics of modern munitions to see what actually happens to organic matter.
Which brings us to Section 2. Blast dynamics and shockwaves.
Let's watch how this builds. In just the first few microseconds of detonation, the chemical bonds inside the explosive material break apart violently. Then, within milliseconds, this triggers a massive gas expansion. We're talking hundreds of times the original volume of the explosive. And in the subsequent milliseconds, an extreme heat and pressure wave violently impacts the immediate surroundings. It's literally an instantaneous transformation from a solid weapon into a supersonic, hyperdestructive thermal wave.
Now let's move to Section 3, aluminum's role in explosives.
Let's compare these two main types of explosives. Traditional explosives like tritonol or TNT rely primarily on a short, intense mechanical shock to shatter their targets. However, modern thermobaric mixtures such as FX757 rely on an extended thermal vacuum. By adding fine aluminum powder into the explosive mix, the physics fundamentally change. The aluminum combusts with the surrounding oxygen, and this vastly extends both the duration and the intensity of that thermal wave. That addition of aluminum powder pushes the core temperature of the resulting fireball to over 3,000 degrees Celsius. To put that staggering number into perspective for a second, that is hot enough to melt solid steel and liquefy heavy metals in an absolute instant. It's almost hard to wrap your head around.
Moving right along to Section 4, the Mark 80 bomb family.
And this brilliantly illustrates the sheer physical scale we're talking about here. Take the Mk-84 aerial bomb from the Mark 80 series. It weighs nearly 2,000 pounds. These massive munitions are frequently equipped with those AFX757 thermobaric aluminum-rich charges we just talked about. That upgrade basically transforms them from standard bombs into immense, highly destructive thermal weapons. Notice how the Mark 80 family scales up. It starts with the Mk-81 at around 250 pounds, moves up to the Mk-82 and Mk-83, all the way up to that massive Mk-84. As the sizes go up, the explosive payload often shifts from traditional tritonol over to those AFX757 mixtures in the modified versions. And naturally, scaling up the bomb weight exponentially scales up both the biological and the structural devastation at the blast center.
All right, on to Section 5, thermobaric versus traditional explosives.
Now, what's really interesting about this is how a thermobaric blast breaks down into 4 concentric physical zones. Zone 1 is the blast center, where we see total atomization and the melting of heavy metals. Zone 2 is the shock range, which is characterized by intense heat that vaporizes liquids instantly. Then there's Zone 3, the fragmentation range, where the pressure pulverizes solid concrete into dust. And finally, Zone 4 is the projection range, where the wave has weakened just enough to throw objects and bodies rather than completely disintegrating them.
Looking a little closer at the actual mechanics of thermobaric or vacuum weapons, they work in this brutal, rapid sequence. First, they disperse a highly volatile explosive cloud into the air. Next, a secondary charge ignites that cloud. This instantly consumes all the surrounding oxygen, creating a massive, extended fireball and a deadly negative pressure vacuum. This sudden, absolute deprivation of oxygen is a huge factor that contributes to the rapid destruction of biological tissue.
Which leads us to our final part, Section 6, the explosion's impacts on the body. So at a baseline, our bodies are roughly 60 to 70% water and about 12 to 15% bone mass. Because we have such an incredibly high water content, the human body is deeply, deeply susceptible to the extreme heat waves we mentioned earlier. When water is subjected to 3,000 degrees, it flash boils in milliseconds, causing tissue to catastrophically rupture.
But what about our bones? Well, human bone is actually incredibly resilient. In fact, a single cubic inch of human bone can naturally withstand 8.6 tons of pressure. That's a remarkable biological feat of structural engineering, beautifully designed to take the impacts of daily life.
So, the absolutely crucial point here is this. Despite the immense natural strength of human bone, the physical forces of an Mk84 thermobaric blast completely surpass biological limits. Total atomization occurs because the combination of 3,000-degree heat, extreme negative pressure, and instant oxygen deprivation forces both soft tissue and solid bone to just shatter. The biological mass is turned into microscopic ash, instantly mingling with the pulverized concrete and dust of the surrounding environment.
The scientific report impartially summarizes this grim reality with a quote that really hits the nail on the head. The biological mass of a human is completely transformed into carbon gases and very fine ash, leaving no tissue for DNA extraction. This mathematical thermodynamic truth is exactly what explains that initial colloquial myth of bodies evaporating. They don't just vanish into thin air, they are violently broken down at the microscopic level.
Which really leaves us with a profound and thought-provoking challenge. When modern munitions, fueled by advanced chemistry and thermodynamics, can completely erase physical and genetic evidence, how does forensic science adapt to confirm a life once existed? Thank you so much for joining me on this explainer. Keep asking questions, keep seeking to understand the mechanics of our world, and I'll catch you next time.